All right, so we are talking about something that should be brand new to most of you called logarithms. Logarithms and logarithmic functions. The first thing we're going to do today is just the first half, talking about logarithms. And what's really important to remember is in the last chapter when we talked about finding inverses, because we just talked about exponential functions, and the logarithmic function is actually the inverse of an exponential function. So we're going to be talking about these expressions, how to find them, but first we're going to recap the exponential stuff from the last couple lessons and then talk about what its inverse would look like. So this first line says, consider the exponential function y equals 2 to the x. So we're going to start with y equals 2 to the x and then take a look at what some of its points would look like. Alright, so let's just do the classic, like, negative 2 to 2. Okay, and if we were to plug in some of these points, so remember 2 to the negative second power? 2 to the second power would be 4. If it's the negative second power, it flips it to the denominator. So this would be a 1/4. Okay, so again, because 2 to the second is 4, the negative exponent, 2 to the negative second, would be the reciprocal of 2 to the second power. Same thing with this. The negative exponent means this is the reciprocal of 2 to the first. So 1/2. 2 to the 0, anything raised to the 0 power just gives you 1. 2 to the first, anything to the first power stays the same. And then 2 to the second power would be 4. So just a sample of some values there. So we're going to talk about what its inverse would look like. So remember inverse functions, you literally swap the x and the y. All right, so if we swap the x and y, we would get x equals 2 to the y. And if we're going to swap all the x's and y's right here in the function, we're also going to swap all the x's and y's in our table. Okay, so the x column is now going to be replaced with this y column right here. Hopefully you guys remember doing this on your last test. When you had a list of ordered pairs, you would literally just switch the x and y values. So instead of having the point negative 2 1/4, you have the point 1/4 negative 2. And instead of the point negative 1 1/2, the inverse has the point 1/2 negative 1. So we're just swapping all these points here. So instead of 0 1, we have 1 0. Instead of 1 2, we have 2 1. And instead of 2 4, we have 4 2. All right, so this is a list of the exponential function, 2 to the x, and this is a list of all of its inverse points. Okay, so I'm going to try my best to explain exactly what a logarithm is, and I will admit it's a little bit of a tricky concept that takes some practice, but it's defined as this graph right here, and in general, what this means is you're trying to find a power. It's like you're working backward from what an exponential function does. So in an exponential function, you're given the power, and you just plug it right in and you come up with the answer. For 0, you're given a power. If 0 is the power on this function, your answer is 1. In the inverse function, you're working completely in reverse. In an inverse function, the x value is actually the answer. And what you're trying to find is what power gave you that answer. So you're like, oh, okay, so if x is 1/4, that means 2 to some power gave me an answer of 1/4. It's like, okay, so 2 to what power would give me 1/4? Well, that would be a power of negative 2. Let's look at the last one down here. Same thing. We're considering 4 to be the answer. So if we know 4 is the end result, the y value would be what power gives us an answer of 4. So if 2 is our base, 2 to what power gives us 4? 2 to the second power. If we look at 1, 2 to what power gave us an answer of 1? To 0 power. So it works all the way down the list, and if we extended the table, it would work for that as well. All right, so this function is called the logarithm of x. All right, so in general, that's this inverse right here. So instead of having a power of 2, or I'm sorry, a base of 2, we're just going to write b. That's what we use as a generic notation for whatever the base is. So the logarithm, quick definition here. The logarithm is written like this: y equals log base b of x. And so log is just the notation we use for logarithm. The base b is the same base that you would see up here. All right, so this function right here is actually like log base 2 of x. And what we read this is log base b of x. So no, there's a lot of focus on saying things the correct way, something I've been trying to work with you guys. So when you see this, read it as log base b of x. All right, and so the way that this works, and we're going to take a look at this stuff right here. So logarithm with base b. Let b and x be positive numbers. B can't be 1. The base is never going to be 1 because it wouldn't really be an exciting function at all. If the base was 1, any power gives you an answer of 1. All right, so we don't have a base of 1 for that. So let's take a look at how we kind of relate this function to this function. So let b and x be positive numbers with b not equal to 1. If we're looking for the logarithm of x with base b, like we said, it's denoted like this, log base b of x. And here's how we start off. It says for x greater than 0, which we've already said here, x is going to be greater than 0, it's a positive number. We say there is a number y such that log base b of x is equal to y if and only if, and we talked about what that means in a previous video, if and only if b to the y equals x. Okay, so just like I said up above, you're basically trying to find a missing power. So here, we would say that log base 2 of 4 equals 2. And we say that's true only because 2 to the second power gives us 4. It's going to seem very, very, very weird when we're just looking at b's and y's and x's, so I think it'll help when we're looking at some examples like this. Okay, so this first one right here, log base 4 of 16 equals 2. We're going to practice writing them back and forth from exponential form into logarithmic form and from logarithmic form back into exponential form. So, for example, this one that we're looking at right here is in this form right here. Log base b of x equals y. So I'm just going to mark on here what number is replacing each letter here. So this means that b is 4. So that's b. This means that 16 is the x. And this means that 2 is the y. Okay, so we're going to use the b, the x, and the y and write it in this notation instead. Okay, so we write it like this. B is 4. And then y right here is 2. So we use that as the exponent. And then equals x, so x is 16. And hopefully you're looking at that statement, you're like, oh, well, yeah, that's true. 4 to the second power does in fact give me 16. So if we're just looking at a statement like this, this is saying log base 4 of 16, meaning 4 to what power gives me 16? 2. And then when you rewrite it into exponential form, you can see that that is in fact true, that 4 to the second power does give us 16. Okay, so same thing right here with this one. 3 is our base. 729 is our x value, and then 6 is our y, and so we write it into this form, b to the y equals x. So b, which is 3, to the y power, which is 6, equals 729. Now this one we might not know immediately is true, but we could probably guess. We know 3 to the 4th is 81, so if you multiply by 3 again, you get 243. If you multiply by 3 again, you get 729. So 3 to the 6th power is in fact 729. So let me read it in log form. We say log base 3. Log is basically the same as a power. So this is asking what power of 3 gives us an answer of 729? The 6th power. All right, so now let's go backwards. These are things that should look familiar. You're like, yep, 4 cubed equals 64. And this one we might not be as familiar with, but we'll talk about that. So 4 to the 3rd equals 64. So now we're looking at this notation right here. So in this notation, 4 is b, the base, 3 is y, and then 64 is x. So now we're in this notation, we're trying to write it back in this notation. Okay? So that's going to look like this. We always start with the word log, and then the base comes next, the 4. And the other two just trade places. So if you look here, the base is always the very first number that you're writing, and then the other two will just swap. So here you still write the 4 first, but then you write the 2 and then the 16. And down here, you always write the 4 first, but then you write the 64, and last is the 3. So log base 4 of 64. So again, this is asking what power of 4 gives me an answer of 64? That would be the power of 3. Okay, last one here. I just want to point out to you that this is in fact true. We might have forgotten about the 1/3 power already. Remember, if you raise something to the 1/3 power, it's the same as taking the cube root. All right, so just as a note for you to remember, that is the same as taking the cube root. So they're saying in this statement that the cube root of 125 is 5, which it is. It's like what multiplies by itself 3 times to give me 125? Well, 5. So if we mark all the pieces on here again, 125 is our base, 1/3 is y, our answer, and x. Okay, so let's transform this last one. Log base 125, so remember the base is always the very first number we write, and then it's like we're swapping the other two in order. So the next thing is 5 equals 1/3. We're just putting it into this form. The b goes here, then the x, and then the y, and we've got them all labeled. So again, what power on 125 gives us an answer of 5? That would be a power of 1/3. One thing I want to point out as we start to get into these logs, notice here, we're looking for a missing power here, and we're looking for a missing power here. Here, the power that takes us from 4 to 64. 64 is obviously bigger than 4, so it must have been raised to a whole number power. Here, 125 to 5, that obviously gets smaller. So the only way to go from 125 backward to 5 would be to take some sort of root. And this tells us that we took the cubed root. That's what the 1/3 power means. Okay, so a couple of those we're kind of transforming back and forth between exponential and logarithmic form. We're just going to do a couple more here where we evaluate each logarithmic expression. Okay, so this is where it's really important to remember the ideas that I was saying of the missing power sort of thing. So log base 3 of 81 equals something. We don't know. So what we're trying to figure out is, well, 3 raised to some power gives us 81. Okay, so remember 3 is our base and 81 is like our answer. So this log expression is saying what power on 3 will give me an answer of 81. So that's what I wrote this down here. 3 to what power gives me 81? And I'm hoping that we recognize that. 3 to the 4th power gives us 81. So log base 3 of 81 equals 4. And we can always use what we just practiced on the previous page to put it back into exponential form, and that would be 3 to the 4th equals 81, which hopefully you can confirm is in fact correct. Okay, this one. Our base is 1/2, so this one's going to be a little weird. 1/2 to what power gives us 256? Okay, so 1/2 raised to some power, giving us 256. That one's going to be a little bit weird. What we can do is take this, because 1/2 is not a base that we're used to, but it's actually a power of 2. So what I want to do is transform both of these into powers of 2. All right, so let's get a little bit more formal with this. Instead of a question mark, let's write this as an x and make it like a variable that we're trying to solve for. Okay, so 1/2, instead of 1/2, it's a power of 2. So we're going to write 1/2 is 2 to the negative first. Okay, negative first means it's the reciprocal. So the reciprocal of 2, hopefully you can agree, is 1/2. And then we're raising that to the x power. Okay, equals, and then 256 is a power of 2 as well. You might have to think about that one. So let's think of one that we know. We know 2 to the 5th is 32. So just keep doubling. So 2 to the 5th is 32. 2 to the 6th would be 64. 2 to the 7th would be 128. And 2 to the 8th would be 256. And then this becomes what we were just doing in the previous lesson. Once you get the bases the same, you can just set the powers equal to each other. So if you set negative 1x equal to 8, you can divide both sides by negative 1, and we end up with negative 8. So what that means is that log base 1/2 of 256 gives us negative 8. All right, so this is our official answer, it's just the number on the end. So that means that 1/2 raised to the negative 8th power gives us 256. Okay, so I think we're going to cut it there for now, and then we'll do the graphing part the second half in our next video.